Welcome to today's session. We'll be diving into problem number 800, similar RGB color. In this problem, we'll explore an interesting challenge related to hexadecimal color codes and how to efficiently determine the closest similar RGB color. Let's get started. The problem's similar RGB color focuses on hexadecimal color codes and their shorthand representations. A hexadecimal color code is a 7-character string beginning with a hashtag, followed by 6 hexadecimal digits. These digits are grouped into 3 pairs, each representing one of the red, green, or blue, RGB, color components. Hexadecimal numbers range from 00 to FF, where 00 represents the lowest intensity and FF represents the highest. The shorthand format reduces each 2-digit component to a single digit that is repeated, so 09 becomes 11 and F1 becomes EE. The task is to find the shorthand code that minimizes the squared difference between the given color and the shorthand color for each component. The squared difference is calculated as x, y, 2, where x and y are the numeric values of the hexadecimal numbers. Your final output should be the closest shorthand hexadecimal color code, represented in lowercase. The output of the problem is a single string representing the closest shorthand hexadecimal color code. For example, consider the input color equals #09F166. The solution involves evaluating each component of the color code. For the red component 09, the closest shorthand is 11 because it minimizes the squared difference. For the green component F1, the shorthand EE is closest, and for the blue component 66, it is already in shorthand format. Combining these, the output becomes #11EE66. This process ensures that each color component is converted to its nearest shorthand representation, minimizing the squared difference. In the next example, with input color equals #4E3Fe1, the goal remains the same: find the closest shorthand representation for each color component. For the red component 4E, the shorthand 44 is closest. For the green component 3F, the shorthand 55 is closest. Finally, for the blue component E1, the shorthand EE is closest. Combining these results gives the output #4455E. This illustrates how the squared difference calculation is applied to each component, ensuring the final shorthand code is the most accurate match. Now consider a simpler example, where the input is color equals #ABK. In this case, all components are already in their shorthand forms. The red component is AA, the green component is BB, and the blue component is CC. Since no further transformations are needed, the output remains #ABK. This demonstrates that if the input color is already in shorthand format, the solution will return the input as is, adhering to the problem's constraints. To solve this problem, you need to determine the squared difference between each component of the input color and all possible shorthand values. A shorthand value is formed by repeating a single hexadecimal digit twice, such as 1-11. For example, if the red component is 4E, you must compare it against shorthand values like 00, 11 EFF and select the one with the smallest squared difference. The solution must also handle edge cases, such as when the input color is already in shorthand format or when components are near boundary values, such as #000001. The output should always be returned as a valid lowercase hexadecimal string in the #RRGGBB format. To solve this problem, one approach we can consider is the brute force method, which involves generating all possible shorthand hexadecimal color codes and comparing each one to the given input color to find the closest match. The shorthand codes range from #000 to #FFF, and each of these is expanded to its full 6-digit equivalent, such as #000000 or #111111. For each candidate, we calculate the distance to the input color in RGB space using the formula R1, R2, ℏ2 plus, G1, G2, ℏ2 plus, B1, B2, ℏ2, where the R, G, and B values represent the red, green, and blue components of the colors. The candidate with the smallest distance is considered the closest match. While this approach is straightforward and simple to implement, it requires generating and comparing all 4,096 possible candidates. This makes it computationally expensive and inefficient for real-time applications, even though the total number of comparisons is fixed. The trade-off here is that while the brute force approach is conceptually simple, it introduces significant overhead due to the exhaustive nature of the comparisons. A more efficient solution is the optimized approach, which focuses on each color channel red, green, and blue independently, rather than generating and comparing all possible shorthand color codes. The key insight here is that each shorthand hexadecimal digit, such as A in #AABBCC, corresponds to a repeated pair, like AA. This means we can directly map each channel to its closest shorthand value without evaluating all possible combinations. First, we parse the input color into its R, G, and B components, such as #AABBCC being split into AA, BB, and CC. Each of these is then converted from hexadecimal to decimal, so AA becomes 170, for example. The next step is to find the shorthand value closest to the given decimal number by minimizing the distance, x*17 value, (2), where x ranges from 0 to 15 and represents the possible shorthand digits. Finally, we construct the result by combining the closest shorthand values for all three channels. This approach is highly efficient, as it avoids unnecessary comparisons and operates in constant time. While it's a bit more challenging to implement due to the need for handling hexadecimal arithmetic, the efficiency gains make it well suited for this problem. The optimized approach was ultimately chosen for this problem because of its efficiency and simplicity. By observing that each color channel operates independently and that shorthand hexadecimal codes correspond to multiples of 17, we were able to reduce the problem to a much simpler one, finding the closest multiple of 17 for each channel. This key insight eliminated the need to generate all possible candidates, allowing us to solve the problem in constant time. The breakthrough came from recognizing that the shorthand format inherently provides a linear mapping between 6-digit and 3-digit codes, which simplifies the distance computation significantly. While the implementation requires careful handling of hexadecimal arithmetic, this complexity is a small trade-off when compared to the substantial performance improvements over the brute force method. In summary, the optimized approach strikes the perfect balance between clarity, efficiency, and scalability, making it the ideal solution for this problem. The problem we are solving here involves converting a 6-digit hexadecimal color code into its closest 3-digit shorthand representation. Hexadecimal color codes, such as #1A2B3C, use pairs of digits to represent the red, green, and blue components of a color. The shorthand 3-digit codes simplify this by using a single digit per component, such as #123, which expands back into a full 6-digit code by repeating each digit twice, resulting in #112233. Our goal is to find the shorthand code that, when expanded, is as close as possible to the original 6-digit color in terms of color difference. This problem essentially requires us to minimize the distance between the input color and the expanded shorthand color by choosing the best shorthand representation. To solve this problem, we start by generating all possible shorthand hexadecimal codes. Since each component of the shorthand code red, green, and blue can range from 0 to F in hexadecimal, there are 16 values for each digit. This results in a total of 16 cubed, or 4096, possible shorthand codes, ranging from #000 to #FFF. Each of these shorthand codes is expanded into its 6-digit equivalent by repeating each digit twice. For example, #123 becomes #112233, and #ABC becomes #ABC. After generating these expanded codes, we need to compute the difference between the input color and each expanded shorthand. This involves calculating the squared difference for each color component red, green, and blue. Specifically, we calculate RR*24 red, GG*24 green, and BB*24 blue, where RR, GG, and BB are the input components, and RR, GG, and BB are the shorthand components after expansion. The total difference is the sum of these squared differences, giving us a measure of the color distance in the RGB space. Once we have the differences computed, the next step is to find the shorthand code with the smallest difference. To do this, we iterate through all 4096 shorthand codes. For each code, we expand it to its 6-digit equivalent, compute its difference from the input color, and keep track of the shorthand code that results in the smallest difference. Finally, after evaluating all candidates, we return the shorthand code with the smallest difference as the result. There are a few key insights to note here. First, in hexadecimal representation, each color component ranges from 00 to FF, or 0 to 255 in decimal. The shorthand simplifies this by using only one hexadecimal digit per component. Second, the expansion of a shorthand digit by repeating it ensures that the intensity of the color component remains proportional. The squared difference formula allows us to calculate the Euclidean distance in the RGB color space, which is a natural way to quantify color similarity. Lastly, because there are only 4,096 candidates, this brute force approach is computationally feasible, making it a practical solution to the problem. To implement the algorithm, we use simple data structures to manage the process. The input color #RRGGBB is first parsed into three integers, RR, GG, and BB, representing the red, green, and blue components. To generate the shorthand codes, we use a nested loop that iterates over all combinations of the 16 possible values for R, G, and B. A variable is used to keep track of the minimum difference encountered so far, along with the corresponding shorthand code. There are also a few important edge cases to consider. If the input color is already an expanded shorthand color, such as #112233, the output should directly be its shorthand form, #123. For boundary values like #000000 and #FFFFFF, the algorithm must handle these extremes correctly. In cases where two shorthand codes have the same difference, the one that appears first in generation order, from #000 to #FFF, should be chosen. Regarding complexity, the time complexity is 4096, which is essentially constant because the number of shorthand codes is fixed. The space complexity is also constant, as we only use a few variables for computation and tracking. This makes the algorithm efficient and well suited to the problem at hand. This Python implementation solves LeetCode problem 800, similar RGB color, by finding the closest shorthand 3-digit hexadecimal color for a given 6-digit hexadecimal color. The solution leverages the fact that shorthand colors repeat each digit, e.g., number 123-number 112233. To begin, the similar RGB function is defined, and a helper function, closest_shorthand_component, is created to find the closest shorthand value for a given 2-digit hexadecimal component, e.g., 1A. This helper function converts the input component to its decimal equivalent using int comp 16 and calculates the closest shorthand digit by dividing the decimal value by 17, since 0x11 in hex equals 17 in decimal. The round function ensures the nearest shorthand value is selected. The shorthand value is then clamped to the valid range of 0 to 15 to prevent out-of-bounds values. The result is converted back to a 2-digit hexadecimal string using format quotient *17, 02x. This ensures that the shorthand value is correctly expanded, e.g., number 22. Next, the input color is split into its red, green, and blue components using string slicing, color 1:3, color 3:5, and color 5:7. Each component is passed to the helper function to compute its closest shorthand equivalent. Finally, the shorthand components are concatenated with a hashtag prefix and returned as the result. This implementation ensures that the closest shorthand color is computed efficiently and accurately. Here, we start implementing the solution to find the closest similar RGB color in Java. The main task is to take a given 6-digit hex color code and transform it into its shorthand form, where each component is represented by a single hex digit doubled. To achieve this, we define a helper method called closest shorthand component, which is responsible for finding the closest shorthand value for a given 2-digit hex string. First, we convert the input hex string into its decimal equivalent using integer.parseInt. Then, we calculate the closest shorthand representation by dividing this decimal value by 17, which is the decimal equivalent of the shorthand increment 0x11. Using math.round ensures that the result is rounded to the nearest integer. Since shorthand values are limited to the range 0 to 15, we clamp the result to this range using math.max and math.min. Finally, we convert the shorthand value back to a 2-digit hex string by multiplying it by 17 and formatting it with string.format, ensuring it keeps the proper 2-character format. This method is then used in the similar RGB function, which starts by splitting the 6-digit color code into its red, green, and blue components based on their respective substring positions. The function similar RGB continues by finding the closest shorthand representation for the green and blue components, just as we did for the red component. This is achieved by calling the closest shorthand component method for each of these segments. Once all three shorthand components are calculated, they are combined into a single string to form the final shorthand color code. The result is returned as a new hex color string, prefixed with a hashtag to match the format of the input. This approach ensures that the output is the most visually similar shorthand color to the original input while adhering to the constraints of shorthand RGB codes. The code is concise, readable, and leverages helper methods to keep the logic modular and maintainable. Here, we begin with the input color #09F166. The first step is to break this color into its red, green, and blue components. The red component, R, is extracted as 09. The green component, G, is extracted as F1, and the blue component, B, is extracted as 66. Now, focusing on the red component 09, we convert it from hexadecimal to decimal, giving us 9. To find the closest shorthand representation, we divide this number by 17, which is the step between valid shorthand values, and round the result to get 1. We ensure that this value is within the valid range of 0 to 15, which it already is. Then, we multiply 1 by 17 and convert it back to hexadecimal, resulting in 11. This becomes the shorthand representation for the red component. Next, we process the green component F1. Converting it from hexadecimal to decimal gives us 241. Dividing 241 by 17 and rounding the result gives 14, which is already within the valid range. Multiplying 14 by 17 and converting it back to hexadecimal provides EE, the shorthand representation for the green component. Moving on to the blue component 66, we convert it to decimal, which gives 102. Dividing 102 by 17 and rounding gives 6, which is within the valid range. Multiplying 6 by 17 and converting it back to hexadecimal gives 66, the shorthand representation for blue. Finally, we combine the shorthand values for red, green, and blue to get the resultant color #11EE66. For the first example, the final output is #11EE66. Now, let's look at the second example with the input color #ABCDEF. As before, we start by breaking it into its red, green, and blue components. The red component is AB, the green component is CD, and the blue component is EF. Starting with the red component AB, we convert it to decimal, which results in 171. Dividing 171 by 17 and rounding gives us 10, which is within the valid range. Multiplying 10 by 17 and converting it back to hexadecimal results in AA, the shorthand representation for red. Now, for the green component CD. Converting it to decimal gives 205. Dividing 205 by 17 and rounding results in 12, which is within the valid range. Multiplying 12 by 17 and converting it back to hexadecimal gives CC, the shorthand representation for green. For the blue component EF, converting it to decimal gives 239. Dividing 239 by 17 and rounding gives 14, which is within the valid range. Multiplying 14 by 17 and converting it back to hexadecimal gives EE, the shorthand representation for blue. Combining these shorthand values for red, green, and blue gives us the resulting color #AK. For the second example, the final output is #AK. Now, let's proceed with the third example, where the input color is #123456. As always, we start by parsing this into its red, green, and blue components. The red component is 12, the green component is 34, and the blue component is 56. Starting with the red component 12, we convert it to decimal, which results in 18. Dividing 18 by 17 and rounding gives us 1, which is within the valid range. Multiplying 1 by 17 and converting it back to hexadecimal results in 11, the shorthand representation for red. Next, we process the green component 34. Converting it to decimal gives 52. Dividing 52 by 17 and rounding results in 3, which is within the valid range. Multiplying 3 by 17 and converting it back to hexadecimal gives 33, the shorthand representation for green. For the blue component 56, converting it to decimal gives 86. Dividing 86 by 17 and rounding gives 5, which is within the valid range. Multiplying 5 by 17 and converting it back to hexadecimal gives 55, the shorthand representation for blue. Combining these shorthand values for red, green, and blue gives us the resulting color #113355. The final output for the third example is #113355. To determine the time complexity of the similar RGB function, we begin by analyzing its components step by step. First, the input string color, which is always of fixed length, is sliced into 3 substrings representing the red, green, and blue components, R, G, and B. Each slicing operation is O1, because the string has a constant size of 7 characters. Next, for each of these components, the function closest shorthand component is called. Within this function, converting a 2-character hexadecimal string to an integer using int comp16 is an O1 operation, as the input size is constant. Then, the closest shorthand value is found using division, rounding, and clamping operations, all of which are O1, since they involve simple arithmetic and conditional checks. Finally, converting the result back to a hexadecimal string using format is also O1. Thus, the time complexity of processing one component is O1, and since there are 3 components, the cumulative time for this step is still O1. After processing each component, the results are combined to form the final output string. Concatenating the shorthand representations of the red, green, and blue components into the final string is O1, as the resulting string has a fixed length of 7 characters. Therefore, combining the results does not add any additional complexity. When we sum up all the steps, the function performs O1 operations for each component and combines them in O1 time. As a result, the overall time complexity of the similar RGB function is O1. Moving on to space complexity, the input string color requires O1 space since its length is fixed. Similarly, the substrings R, G, and B occupy O1 space, as they are constant length strings of size 2. Any intermediate variables used inside closest shorthand component, such as the integer number, the quotient, and the shorthand value, also require O1 space. These are all fixed size data, contributing to an overall space complexity of O1. The output of the function, a 7-character string like #112233, is also fixed in size and therefore requires O1 space. Since no additional dynamic memory structures or recursive calls are utilized, the overall space complexity remains O1. To contrast this with a naive approach, consider iterating through all possible shorthand hexadecimal color codes. With 256 possible values for each of the 3 components, R, G, and B, this would require 256 cubed iterations, or 16,777,216 comparisons, to evaluate every possible color combination. While this brute force method uses O1 space, its time complexity would be O256 cubed, which is computationally expensive. In comparison, the optimized approach avoids this inefficiency by directly calculating the closest shorthand value for each component mathematically, reducing the time complexity to O1. This efficiency highlights the strength of the optimized solution. The similar RGB function performs consistently regardless of the input, making its time complexity O1 in all cases. In the best, average, and worst-case scenarios, the function executes the same fixed set of operations. It does not involve any input-dependent loops, conditional branches, or recursive calls that could alter its behavior based on the input. Mathematically, the big O notation remains constant because the number of operations does not scale with the input size. Every step, from slicing the input to processing components and constructing the output, involves a fixed number of operations performed a constant number of times. Similarly, the space complexity remains O1, as no dynamic memory allocation or variable length data structures are used. This ensures that the function is both time efficient and memory efficient, making it a highly optimized solution for the problem at hand. One of the most common mistakes when working with this problem is not expanding shorthand hexadecimal color codes correctly. Shorthand codes like #ABC need to be expanded to their full 6-character form, such as #ABC. Failing to do this or doing it incorrectly can lead to mismatched comparisons and incorrect results. Another issue arises from inefficient comparisons. For instance, brute forcing through all possible combinations from hashtag 000000 to hashtag FFFFFF, instead of leveraging patterns or constraints, can result in excessive computation and poor performance. It's important to optimize wherever possible. Additionally, skipping edge cases is a critical oversight. For example, input strings that are not valid hex codes, like hashtag 12345 or hashtag XYZ, or even empty strings, must be accounted for to make your solution robust. Lastly, case sensitivity can trip up comparisons. Hexadecimal codes are inherently case-insensitive, so you need to normalize both uppercase and lowercase inputs to avoid mismatches, such as treating hashtag ABC and hashtag ABC as different values when they are, in fact, equivalent. Another pitfall is assuming that all input strings are valid hex codes without proper validation. Poor handling of invalid inputs can lead to runtime errors or undefined behavior, which is a critical issue, especially in an interview setting. To address this, you must validate and sanitize inputs before processing. Now, when it comes to interview strategies, focus on identifying patterns in the problem to reduce unnecessary calculations. For example, shorthand hex codes follow specific expansion rules that you can leverage to simplify your approach. Always make sure to account for edge cases, such as empty strings or invalid inputs, as this demonstrates a thorough and robust solution. Efficiency is another key point. While brute force solutions might be acceptable for small input sizes, you should aim to propose more optimal methods, even if you don't implement them fully. Finally, remember to think aloud during interviews. Clearly explaining your thought process can help demonstrate your ability to analyze constraints, simplify the problem, and arrive at effective solutions. This problem also connects to several related problems that can provide additional practice and insight. For example, in LeetCode 771, Jewels and Stones, you focus on pattern matching and efficient comparisons, which is a shared skill. Problem 387, First unique character in a string, emphasizes input validation and efficient string processing, similar to the challenges here. Problem 242, Valid anagram, involves normalization and comparison of strings, while Problem 49, Group anagrams, highlights the importance of handling case sensitivity and edge cases. Additionally, there are alternative approaches to this problem that you might consider. For instance, an optimized iterative approach allows you to directly compare expanded forms of shorthand hex codes without generating all possible combinations. This improves efficiency but requires a solid understanding of the expansion rules. Another option is using hashing for quick lookups. By storing expanded forms in a hash set, you can achieve constant time lookups, though this comes with additional space complexity. Lastly, regular expressions can be employed to validate input before processing. While this adds a slight learning curve, regex ensures robust and reliable validation, which can significantly enhance your solution. Thank you for joining today's session. To recap, we discussed finding the closest shorthand hexadecimal RGB color, touched on a brute force approach, and highlighted the importance of optimization. Remember to practice similar problems to solidify your understanding. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!